So in previous lecture we already talked about the operators, and we have already seen about the position operator and the momentum operator, and we have derived the momentum operator while taking a wave function psi. So that was equals to 1 upon root 2 pi h and e to the power I by h v naught x. Right. So this was our wave function, and from there we have derived a linear momentum operator P that was equals to minus Ix del by del x, and this linear momentum operator is a first order derivative. Okay. So in today's lecture, I'll be talking about the properties of operators. So like in function, let's say if you add two functions, that gives you another function, that is the third function. Or if you multiply two functions, that gives you the another function, that is the third function. So as like in the function, the operation that we do, we can perform the that kind of similar operation in the operator as well. So let's say if we have two operators A and B, and so here I will talk about properties of operator. So let's say we assume a wave function psi, that psi can be anything that you can assume, and if we have two operators A and we do the summation of these two operators, this is the first property, and if we add these two operators and the addition of these two operators is working on the wave function psi, so here you will get this formula A psi plus B psi. Is that clear? So second thing is that let's say the same formula, if and this operator A is being multiplied with a scalar quantity small a, and this B, that is a scalar quantity that is being multiplied with operator, and if it is acting over a psi, then that will give you A operated over psi, then B, which is being multiplied with operator B, which is being operated over the psi. Right, so this was the addition. Similarly, it can be multiplication as well, subtraction as well. So if your operator A that is being subtracted to B, so that is operated over a wave function psi, that will give you A psi minus B psi. And the fourth will be, let's say, this operator A, which is multiplied with the scalar quantity A, and B, which is multiplied with the scalar quantity B, which is being multiplied with psi, then that will give you A, which is operated over the psi, minus B, which is operated over the psi. So it is same like a function that will operate this kind of linear algebra thing in a function. Now coming to the multiplication operators. So if we have a multiplication operator that is filled, so if A, two operators which is being multiplied with this, so that can be written as A, B will operate over the wave function psi, something like that. It's very important. We will see these things, that why this operator is very important. So if we talk about this operator's multiplication and all, so just try to understand some using some fundamental relations. So let's say what I have told you. So if operator X is acting over a wave function psi, so X is the position operator, so that is giving you position of the particle and then psi, and then operator P, which is operating over a wave function psi, that is giving you P naught and psi. Is that clear? So if I want to take a real example of this position and momentum operator, and then see how this is act accordingly. So if we add here these two operators, so if we add position operator with momentum, and so if I want to perform multiplication of this operator, something like that, so what will happen here, it will be like X that will operate on P over psi, right? And what is the position operator, momentum operator, that is your minus I H del by del x. So just try to do these things. So x minus I x del x of psi. So this will give you a value, that is the position operator, that is your minus I h, and then del psi by del x. So finally you will be getting, and what is the position operator does? So you just basically multiply with the position of the particle. So here this is a small x minus I h del psi by del x. So that will give you the value of minus I h x del psi by del x. And what is this value? So when you are doing this x p, that is being operating over the side. Now coming to another, if it is like position operator, sorry, momentum operator multiplied with position operator, that is operating over a side. So here you can write t, then first of x side. And what is x side? So basically you will do multiplication like x of side. Right. Now you have to operate here with position operator, so momentum operator. So that is minus h del x of side. So then you can have this simple mathematics here. So x del psi by del x plus psi del x by del x. So that can be written as simply minus I x del psi by del x plus psi. So if you expand these things, then you can write minus I x del psi by del x minus I x psi. So you are getting these things for when px is operating over a side. Now let's try to do one thing. You try to subtract this. If we do xp over a side minus px over a side, so what you will get? Xp over side is minus IH x del psi by del x. And what is the px over a side? So that will be equals to, if you subtract these things, that will be plus IH del psi by IHX del psi by del x, and that will be also plus IH psi. So this value will get cancelled out, and finally you will be getting xp over the side minus px over the side, we will be getting IX psi. So it's very important concept here that you can say. Now directly I can write these things like xp minus px over a psi, that will give you IH psi. So this is another operator that you have evaluated here while doing this calculation, and that is called as the commutator operator, xp. Right, xp can be written as your xp minus px. Right. So here what we are doing, commutator operator, which is operating over a function psi, that is giving you a value of IH of psi. Is that clear? So what do you mean by these things? It's very important when we talk about the quantum mechanics. So if you see this operator, how this operator is acting and what value you are getting. So if two operators, the commutator of two operator is 0, and if commutator of two operator is not 0, then that is called as non-commutating operator. So let's say if two operator A and B, then I'll come to the position and momentum operator. So if the commutator of two operator that is equals to 0, then that is called as the non-commutating. Means the operators A and B are not commutating with each other, right? So that is called as non. And I'll tell you these things why this is important here. If A cap and B cap is not equals to 0, then that is called as a right. So in this case, what we have observed, the position operator and momentum operator, which is not equals to 0, that is equals to IH. Is that clear? That means the position operator and momentum operator are not commutating with each other. That means what is important and what is the physical significance of this commutating? That means you should have a particular eigenfunction, and from that particular eigenfunction you should calculate the property of the wave function, like its position and momentum. So in this case, if you have a wave function or if you have eigenfunction, and from this eigenfunction you cannot calculate the property like position and momentum of the particle at a particular instant, that means simultaneously. So there will be some kind of uncertainties that will be there if the property or if the operator does not follow the commutating law, right? So we'll see in the next example about the about the linear momentum and kinetic energy operator, whether they are commutating or non-commutating, and we'll tell you that that is directly related to the wave function, eigenfunction. If eigenfunction are common, then directly you can, because if let's say if commutating are not zero, then in that case your operator is not commutating with each other, and if they are not commutating with each other, then they won't be sharing the same eigenfunction. And if you know the eigenfunction also, then you cannot calculate the value of x and value of momentum particularly at a particular instant with accuracy, right? But that will be the another case when we will be talking about the linear momentum operator and kinetic energy operator, because they are commutating operator, and in that case you will be able to calculate the kinetic energy and momentum, linear momentum from the same eigenfunction at a particular instant and with the accuracy. That is the physical significance of understanding the commutating and non-commutating of the operators in the quantum mechanics. Okay, thank you.